The perfect designed F1 car. Imagine a machine so perfectly engineered that it can corner at forces that would make a fighter pilot blackout. A vehicle that generates enough downforce at top speed to theoretically drive upside down on a tunnel ceiling. This isn't science fiction. This is Formula One. And today we're designing the perfect F1 car. But here's the problem. Perfection in F1 is a moving target. What makes a car dominant one season becomes obsolete the next. So how do you create something perfect when the rules constantly change, when your competitors never sleep, and when the difference between first and 10th place can be measured in thousandths of a second? Let's build it from the ground up. And trust me, by the end of this, you'll never look at an F1 car the same way again. The foundation, the chassis. Everything starts with the chassis. And this is where our perfect design faces its first impossible challenge. You need something that's incredibly light. We're talking about a minimum weight of 798 kilograms with the driver. But it also needs to be strong enough to protect a human being in a 200-mile-per-hour impact. The solution? Carbon fiber. But not just any carbon fiber. We're talking about aerospace-grade composite materials layered in specific orientations, with each ply calculated to handle precise stress vectors. The monocoque that forms the driver's survival cell can be up to 12 layers thick in critical areas. Teams literally bake these structures in massive autoclaves, curing them at exact temperatures and pressures. Here's what blows my mind. That carbon fiber tub is so strong that in a head-on crash, the deceleration forces can exceed 100 to 80 G. The car disintegrates by design, absorbing energy. But the survival cell, it remains intact. Drivers have walked away from impacts that tore their cars in half. But strength alone isn't enough. The chassis is the skeleton upon which everything else mounts. It needs mounting points for the engine, the suspension, the aerodynamic elements. Each connection point is a potential failure point, so engineers use finite element analysis to map every stress, every vibration, every load case. And here's where it gets really interesting. The chassis itself generates downforce. The floor of the car, that flat carbon surface you barely notice, is actually sculpted with incredible precision. Modern F1 cars use ground effect, channeling air underneath the car through carefully shaped tunnels. This creates a low-pressure zone that literally sucks the car to the track. The heart, power unit perfection. Now let's talk about power. Our perfect F1 car needs an engine, but calling it just an engine is like calling a smartphone just a phone. This is a hybrid power unit, and it's one of the most sophisticated pieces of machinery ever created for motorsport. At its core sits a 1.6-liter V6 turbocharged engine. Yes, 1.6 liters, the same displacement as many economy cars, except this one produces over 1,000 horsepower and revs to 15,000 RPM. How? Turbocharging, advanced fuel injection, and engineering tolerances measured in microns. The turbo itself is a technological marvel. It spins it up to 125,000 RPM. That's faster than a dentist's drill. And here's the clever part. The turbo isn't just for power. It's connected to the MGU H, the motor generator unit, heat. This device can either harvest energy from the exhaust gases or use electrical energy to spin up the turbo, eliminating lag completely. Then there's the MGU K, the kinetic energy recovery system. Every time the driver brakes, this device acts as a generator, converting kinetic energy into electrical energy stored in a battery pack. Then, on acceleration, it acts as a motor, adding an extra 160 horsepower for up to 33 seconds per lap. Think about what this means. The perfect F1 car isn't just burning fuel. It's a rolling energy management system, constantly harvesting, storing, and deploying power. Drivers have multiple battery deployment modes. Engineers monitor energy levels lap by lap. It's chess at 200 miles per hour. But power means nothing without control, which brings us to perhaps the most critical system of all, the contact patch. Tires and suspension. Here's a fact that should terrify you. All the power, all the downforce, all the engineering brilliance comes down to 4 contact patches, roughly the size of your hand. That's it. That's all that connects this million-dollar machine to the asphalt. Pirelli supplies all F1 teams with the same tires, but the teams must make them work. And this is where suspension design becomes an art form. The perfect F1 car needs suspension that's stiff enough to maintain precise aerodynamic ride height, but compliant enough to keep those tires in contact with imperfect track surfaces. Modern F1 suspension uses pushrods or pullrods connected to torsion bars and dampers hidden inside the chassis. Why hide them? Aerodynamics, everything, and I mean everything, is about managing airflow. The suspension arms themselves are sculpted airfoils, generating downforce even as they control wheel movement. And the geometry is insane. Engineers adjust camber, toe, caster, and ride height to fractions of a degree. A half-degree change in front camber can be worth a tenth of a second per lap. Multiply that over a race distance, and you're talking about track position. Championships, the tire management strategy is equally complex. F1 tires have a operating temperature window. Too cold, they don't grip. Too hot, they degrade. Teams use tire blankets in the garage to preheat them. Drivers weave on formation laps to maintain temperature. The first lap on fresh tires offers peak grip. Then, it's a slow decline over 20, 30, maybe 40 laps depending on the compound. Our perfect car needs suspension that loads the tires correctly through every corner type. Fast corners need stability, slow corners need rotation. The car must roll, pitch, and yaw just enough, but never too much. It's a balancing act that teams spend millions to perfect. The invisible force, aerodynamics. If the engine is the heart of an F1 car, aerodynamics is its soul. And this is where things get truly wild. Modern F1 cars generate more downforce than they weigh. At 150 miles per hour, the downforce exceeds the car's mass. This means that, theoretically, if you built a tunnel ceiling and got the car up to speed, it could drive upside down. The tires would stay planted on the ceiling. Physics is insane. But generating downforce is only half the battle. You need to manage the air over, around, and under the car. The front wing is your first tool. It conditions the airflow, directing it around the front tires and along the car's flanks. Teams bring different front wing specifications to different tracks. High downforce for Monaco's tight corners. Low drag for Monza's long straights. The floor and diffuser are where the magic happens. Remember that ground effect we mentioned? The floor has tunnels sculpted into it, accelerating air as it passes underneath. When air speeds up, pressure drops. That pressure differential creates suction. The diffuser at the rear gradually expands this airflow, recovering pressure while maintaining downforce. Then there's the rear wing. Unlike road cars, where wings are often cosmetic, F1 rear wings generate hundreds of kilograms of downforce, but they also create drag. So engineers use DRS, the drag reduction system. When activated, the rear wing's main plane tilts, reducing drag and increasing straight-line speed by 10 to 15 kilometers per hour. But here's the brutal truth. All this downforce only works in clean air. Follow another car closely, and you enter their turbulent wake. Your front wing loses efficiency. Downforce drops. Lap times suffer. This is why overtaking is so difficult despite massive power and performance. Our perfect car needs aerodynamics that are not just efficient in isolation, but robust in traffic. It needs a balance between peak downforce and raceable characteristics. It needs to be fast everywhere, not just on qualifying laps. The brain, electronics, and strategy. Strip away the carbon fiber and the horsepower, and you'll find something unexpected. The perfect F1 car is a computer that happens to have wheels. The steering wheel alone has over 20 buttons and switches. Drivers adjust brake bias corner by corner. They change differential settings. They manage battery deployment. They adjust tire temperature by altering brake balance. This isn't just driving, this is systems management at race speed. But the driver only sees a fraction of the data. Back in the garage, engineers monitor hundreds of sensors. Tire temperatures at multiple points, brake disc temperatures, oil pressures, battery state of charge, downforce levels calculated from suspension loads. Every system is watched, every parameter optimized. Strategy becomes the ultimate chess match. When do you pit? Which tire compound? Can you undercut the car head by pitting a lap early? Should you overcut by staying out on worn tires? What if it rains? The perfect car needs reliability. A mechanical failure means 0 points, no matter how fast you were. Teams run simulations on every component. They test materials beyond their operational limits. They build redundancy into critical systems. And yet, despite all this technology, the human element remains. The driver must push to the absolute limit without exceeding it. They must manage 20 different systems while fighting wheel to wheel at speeds that would make most people's knees buckle. The reality. Perfection is impossible, so we've designed our perfect F1 car. Carbon fiber chassis for strength and lightness, a 1,000 horsepower hybrid power unit, sophisticated suspension to maximize tire performance aerodynamics that generate massive downforce, electronics to manage it all. But here's the truth, this perfect car doesn't exist. It can't exist. Because F1 is about compromise. Every design choice creates trade-offs. Add downforce, you add drag. Strengthen the chassis, you add weight. Optimize for one track, you sacrifice at another. The regulations change constantly, forcing teams to rethink everything. The teams that dominate are the ones that make the best compromises. They find elegant solutions to impossible problems. They exploit loopholes in regulations until those loopholes are closed. They innovate relentlessly because standing still means falling behind. Red Bull's ground effect mastery. Mercedes' hybrid aerodominance. Ferrari's engine innovations. McLaren's return to form. Each team is chasing that same impossible goal, perfection. And maybe that's the point. The perfect F1 car isn't a destination. It's a direction. It's the relentless pursuit of marginal gains, the obsessive refinement of every detail, the unwillingness to accept that something can't be improved. The next time you watch an F1 race, remember those cars represent the absolute cutting edge of automotive engineering. Thousands of people worked thousands of hours to find thousandths of a second. Every component justified, every gram accounted for, every surface optimized. That's not just racing. That's human ambition crystallized into carbon fiber and titanium. That's what happens when the word impossible becomes a challenge rather than a barrier. The perfect F1 car, it'll always be just out of reach. And that's exactly what makes Formula One so magnificent.